everyone. Let's wait for 5 minutes before we start this session. Okay, so today we will be discussing some problems of week 8 assignment sheet, which mainly involves problems related to the Riemann integration and Riemann-Steltjes integration. So let's start with first question. Question number 1. Let f from AB to R be continuous and G from close AB to R is defined as gx equals to x square. Now clearly this function g is an increasing function provided a and b are positive. Okay. State whether true or false this integral a to b fx dgx, this what we call the Riemann-Steltjes integration. This exists if and only if the Riemann integral of the function f exists. That means we are kind of looking at the equivalence of both the type of integrals. So let me just recall the difference between the Riemann and Riemann-Steltjes integral. So we have seen that this, we say a b fx dx is finite in via two approaches, either by UPF LPF or by the Riemann sum. In this case, for any epsilon positive, there exists delta positive such that UPF minus LPF, this is less than epsilon whenever this norm of the partition P is less than delta, where UPF is the upper sum Mi xi minus xi minus 1. LPF is the lower sum Ni small ni. Summation I from 1 to n mi xi minus xi minus 1, where P is the partition with a equals to x naught less than x1, so on up till xn, which is equal to B. And the small mi and capital Mi are the infimum and supremum of the function f in the subinterval xi minus 1 to xi. So this is small mi is equal to infimum fx, where xi minus 1 less than equal to x less than equal to xi, and capital Mi is supremum fx for xi minus 1 less than equal to x less than equal to xi. So this is one of the method to check the integrability. And the second one is via the Riemann sum, where we say that limit norm p tending to 0 SPF, this is finite. That is, there exists some, say a, some real number, such that for any epsilon positive, we can find delta positive such that this mod SPF minus A, this is less than epsilon, whenever norm P is less than delta. And here, this SPF is called the Riemann sum, which is equal to summation I from 1 to n FCI xi minus 1, where Ci is arbitrarily chosen from the interval xi minus 1 to xi. Next comes the notion of Riemann-Steltjes integration. So we write it as a to b fx d alpha x is finite, where this alpha is an monotonically increasing function defined on closed interval a to b. And we say that this sum is finite. Only the difference would be while taking this upper sum and lower sum, instead of xi minus 1, we'll be taking alpha xi minus 1. So in that case, again, everything will be same. For epsilon positive, there exists some delta positive such that this UPF alpha minus LPF alpha, this is less than epsilon whenever this norm is less than delta, where this UPF alpha corresponding to some partition P, this is equal to summation I from 1 to n, capital MI, alpha xi minus alpha xi minus, and LPF alpha, this is equal to summation I from 1 to n, small mi, alpha xi minus alpha xi minus. So this is the main difference. So via the UPF LPF approach, we take supremum and infimum. Via the Riemann sum approach, we take the value of function at any specific point in the interval. And while looking for the Riemann-Steltjes integral, this xi minus 1 is replaced by alpha xi minus alpha xi minus 1. So the problem says that if f is a continuous function and g is a fixed function, gx equals to x squared, clearly that's why I said this is increasing when ab is positive. We need to see that this integral exists if and only if the function f is Riemann integrable. So clearly we know that since f is continuous, defined on closed and bounded interval, it eventually becomes uniformly continuous, and hence we know we had already done those results that it will be Riemann integrable. So one side is directly clear. Even if this is finite or not, we all know that this will always be finite. So the converse part would be to check that if the function is Riemann integrable, then will it be Riemann-Steltjes integrable as well or not? So let's see. Solution. Now since f defined from AB to R is continuous and closed interval AB is closed and bounded domain, I think we did this type of problem in previous session, that on compact domain, continuous function will always be integrable, closed and bounded. This will give us that f is uniformly continuous. Let's see how we will use that. This implies for any partition P such that its norm is less than delta, we will get UPF minus LPF. This will be summation I from 1 to n, mi minus mi, xi minus xi minus 1. Now, since f is continuous, defined on closed and bounded interval, we know that it will always attain its maximum and minimum. Therefore, for every interval xi minus 1 to xi, we can find xi prime and xi double prime such that this capital Mi is exactly equal to fx prime and small mi is equal to fx double prime. So I'll write that. Since f is continuous, this implies for every I, there exists xi prime and xi double prime belonging to the interval xi minus 1 to xi, such that we all know that the continuous functions always attains its maximum and minimum. That's why instead of supremum and infimum, for the case of continuous functions, we call them maximum and minimum, such that capital Mi is equal to fxi and small mi is equal to fxi double prime. So this gives us, this implies UPF minus LPF. This is equal to summation I from 1 to n fxi prime minus fxi double prime times xi minus xi minus 1. Now, since norm p is less than delta, that means uh, mod f that means mod xi minus xi minus 1 is less than delta. So by uniform continuity, this will be less than epsilon. So eventually, that means we should have taken this delta specific corresponding to the uniform continuity. This, so from here, this implies for epsilon positive, there exists delta positive such that mod fx minus fy, this is less than epsilon whenever mod x minus y is less than delta. Now, since norm p is less than delta, this implies mod xi minus xi minus 1 will be less than delta for every I 1 to up till n. So we are taking exactly the same delta. So if I mark this as this one as 1 and this one as 2, so I can write this to be strictly less than summation I from 1 to n epsilon times in fact, I should write this because the difference between in between terms will always be less than equal to the is less than equal to capital M minus small m summation I from 1 to n xi minus xi minus 1, because obviously the difference between the maximum and infimum will always be greater than the difference between in between values, and again by uniform continuity this will be equal to sum fx bar minus fx double bar, and this is equal to b minus a. So instead of just epsilon, I could take upon b minus a here. I can always do that. So this will be less than epsilon upon b minus a times. No. not say directly, because we should have xi minus xi prime to be less than delta. No? So from here, this will be summation I from 1 to n epsilon upon b minus a times xi minus 1, because mod xi prime minus xi double prime, this is less than delta. So using hence using equation 1. Okay, now it's fine. So this will be epsilon by b minus a, and that sum will be b minus a. Therefore, for any partition P, therefore we get UPF minus LPF less than epsilon whenever this norm P is less than delta. Therefore, P is integrable and a to b fx dx exists. Now, next we need to see conversely. In fact, this part was independent of the fact that it will be Riemann-Steltjes integrable, because we were already given that the function is continuous. For the converse part, we will have to use that. Conversely, let a to b fx dx be finite, and we need to show that it is Rs integrable. That means a to b fx dgx is finite. That is, f is, I'll just write Rs integrable. Okay, so let's see how we will prove that. Now, since this is Riemann integrable, by first, again, for any epsilon positive, there exists delta positive such that UPF minus LPF is less than epsilon whenever norm P is less than delta. Now let's take it specifically. Let P equals to x naught, x1, x2, xn equals to b be a partition of AB such that norm P is less than delta. Now let's see our UPF G minus LPF G. That's what we need to show now. We need to show that this UPF G minus LPF G is less than epsilon whenever norm P is less than delta. So this now UPF G minus LPF G, by definition this is summation I from 1 to n mi minus mi gxi minus gxi. So what is gxi? Gxi is just xi square. So this is summation I from 1 to n mi minus mi xi square minus xi minus 1 square. Now use the identity. A square minus b square is nothing but a plus b, a minus b. So this will be summation I from 1 to n m minus mi xi plus 1 plus xi plus 1, sorry, xi minus 1, xi minus 1 times xi minus xi minus 1. So I can write this to be less than equal to 2m summation I from 1 to n mi minus mi, or instead 2b, no? Because xi and xi plus 1 both are less than b. Xi minus xi minus 1. Because see, xi plus xi minus 1 is less than b plus b, obviously because we are taking xi to be in the interval, closed interval ab, and rest of the terms are positive, so we can easily multiply them because capital Mi is this is something supremum minus infimum, so obviously it will always be positive. Then xi minus 1 is also positive, so this will be less than equal to 2b. Happened. Hmm. xi minus 1 and capital Mi minus small mi, and this happens for every I 1 to 2 n. Okay. So if I take this to be upon 2b, we'll get epsilon over there. So I'm writing this all the necessary things later so that you understand why do we start with epsilon by 2b. Okay, so this will be equal to 2b. And what is this? This is just UPF minus LPF because Mi is again the supremum of the function f over the interval xi minus 1 to xi. So that's the same thing. Only difference was the term here that is tackled up till here. So this is just UPF minus LPF. Now, since the this norm of partition P is less than delta, if I mark this as equation 2, by equation 2, we get this to be less than 2b epsilon by 2b by equation 2. That means UPF G minus LPF G, this is less than epsilon whenever this norm P is less than delta. That means this A to B fx dgx is finite, or we say that f is Rs integral. Therefore, the given statement is true because we get both sides. I hope the solution is fine. If you have any doubt at any step, please ask. The definition of Riemann integrability, Rs integrability, how eventually in the case of continuous functions, this turns out to be same. Now, please go through the solution once again. I'll wait for 5 minutes. If you have any doubt, you can ask. Otherwise, then we'll move to next question. Okay, let's move to next question. Question number two. State whether true or false. Let f and g with two functions defined from closed interval a b to r be such that integral a to b f x d g x is finite. That means f is r is integrable with respect to the function g. Then they're saying that f is bounded if and only if g is continuous. Now, if you can recall the results that were discussed in the class, it was said that if f is bounded, then in order for f to be Rs integrable with respect to the function g should be continuous at the discontinuities of f. So it needs to be continuous only at the discontinuities of the function f. That means the function g need not necessarily be continuous everywhere at discontinuities of f. Now this gives us an idea that this might not be true. Otherwise, the result would have been something else, no? If it was discussed in the class that such a result holds, that means this continuity of G need not necessarily be required to be everywhere. So we can't give such statements in order to prove something. So instead, if I'm saying that this statement is false, then I should be able to give some example, some counter example. So that means if I am able to show that there exists a function f and g where g is not continuous completely on the closed interval ab, and f is a bounded function, still the integral fx dgx is turning out to be finite. So I need to build up some example which satisfies this kind of condition. Then only I'll be able to say that the given statement is false, because we have a function g. We can find a function g which is not continuous everywhere in the closed interval ab, but still the function f being just bounded, f need not necessarily be continuous. F is just a bounded function and g is not even continuous. Then also the function f is Rs integrable with respect to the function g. So you can cook up some examples yourself. The one that I had used is as follows. If we consider this interval, close interval AB to be just close interval 0 to 2, consider A equals to 0, B equals to 2. We define functions f and g from 0, comma 2 to r as follows. This function fx, this is equal to the function x. So clearly this function f is bounded. That's the only requirement according to the problem, that f is bounded on close 0 to 2. They're saying that if it is bounded if and only if g is continuous, but we can say that even if f is bounded, g need not be continuous. So I'll cook up an example of the function g which is not continuous. I take it to be the greatest integer function. That means this is equal to 0 when 0 less than equal to x less than 1. This is equal to 1, 1 less than equal to x less than 2, and 2 when x is equal to 2. So obviously this function g is not continuous. G is not, because it has discontinuities at 1 and 2. It's not continuous on closed interval 0 to 2. So, but still, we claim that this function f is Rs integrable with respect to the function g. That means 0 to 2 fx dgx is finite. That means for there exists some a, or instead, yeah, not a, we're not using it. That means for any epsilon positive, there exists a delta positive such that this UPFG minus LPFG, this is less than epsilon, whenever this norm P is less than delta. Whenever P is a partition such that its norm is less than delta, in that case, this UPFG minus LPFG can be made as small as we want. Okay, so for this specific example of F and G, let's calculate our UPF and LPFG. So now let P, which is equal to 0, x naught, x1, x2, and so on up till xn, which is equal to 2, be a partition of closed interval 0 to 2 such that its norm is less than delta and sum of its element, the jth element of this partition, is exactly equal to 1. So I can always take such an, if we plot this function, this will be 0 to 1, 1 to 2, 2. So I can always cook up for such a partition. All I need to take care of is the fact that this point 1 is taken in the partition and 0 and 2 are always in the partition. I can make it as finer as I want. Okay. And some jth element is equal to 1 for some j. Obviously, this is not equal to 0, so we can start it from 1 to n minus 1. Sum of the element in the partition is equal to 1. Now, this implies what will be our gxi minus 1. So, gxi minus gxi minus 1. So, this is, if you look at the graph of the function g, you can see that if xi and xi minus 1 both are strictly less than 1, then obviously both the values are 0. So that means this is equal to 0 when I is less than, sorry, yeah, greater than equal to 0, because, no, not equal to 0. I is starting from 1, no? 1 less than equal to I, and, sorry, j. For xi to be strictly less than j, this will be up till gxj minus gxi j minus 1. Now gxj is 1. Yeah. For I equal to j, we know that gxj will be equal to 1. This implies gxj is equal to 1. And since gxj minus 1 is strictly less than 1, so gxj minus 1 will be equal to 0. So this is equal to 1 when I equal to j. And after that also, both the values are equal. So up till uh, um, xn, because xn is 2, at that point the difference will again be 1. So this will be equal to 0 when j strictly less than I strictly less than n, and this will be equal to 1 when I equal to n. So that gives us, this implies summation I from 1 to n gxi minus gxi minus 1. This is just gxj minus gxj minus 1 plus gxn minus gxn minus 1, which is equal to 1. And gxn will be 2 and gxn minus 1 will be 1. So the difference will be again 1. So this is equal to 2. Now that means our UPFG minus LPFG, let me mark this as 1. This implies UPFG minus LPFG will be, this is equal to summation I from 1 to n mi minus small mi gxi minus gxi minus 1. So since this difference is always 0 except for I equals to j and n, so this is just mj minus mj times 1 plus m n minus small. So this will be obviously less than equal to the supremum and infimum of the function f on the closed interval b. So closed interval a to b. So this is always less than equal to b minus a plus b minus a. Why? Because fx is equal to x, na? That means the supremum over xi minus 1 to xi fx will actually be equal to xi, na? And this infimum from xi minus 1 to xi of the function fx, this will be xi minus 1. So that gives us that mj minus small mj, this is equal to xi minus 1. So if this is a, this is b, somewhere xi minus 1 and xi, obviously the difference between these two is lesser than b minus a. So this will be less than equal to b minus a. Similarly, this mn minus mn will be less than b minus a. So that gives us this UPFG minus LPFG is less than 2 times b minus a. I should be able to get somewhere epsilon, no? Yeah, I think did a mistake. So here I should use the fact that the function fx is exactly equal to x. So this will be summation I from 1 to n xi minus 1, because the infimum is xi minus 1 and the supremum is xi, times gxi minus 1. So this will be equal to just xj minus 1 times 1 plus xn minus 1 times 1. Yeah. Now, since the norm of the partition P is less than delta, this will be less than delta. This is less than delta. Taking delta to be equal to epsilon, so this will be less than epsilon, or norm P less than delta. Yeah, because obviously this is less than equal to the sum and yeah, eventually the norm. So that means for epsilon positive, there exists delta which is equal to epsilon positive, such that UPFG minus LPFG, this is less than epsilon whenever norm P is less than delta. Now that tells us that this F is actually RS integral. That means 0 to 2 Fx dgx is finite even when F is bounded and G is not continuous. But they were saying that if this is finite, then this can happen when F is bounded if and only if G is continuous. That means this will be bounded only when both the condition holds simultaneously, that the function F is bounded and G is continuous. But we had shown that this is not true. There exists some F in G such that F is bounded but G is not continuous. Therefore, the given statement is false. I hope this proof is fine with everyone. If you have any doubt, you can ask. Please go through the solution once again. Okay, if there is no doubt, we can move to next problem. Question number 3. Again, state whether true or false. if a function is Rs integrable on closed interval AB with respect to some monotonically increasing polynomial function. The function that we are taking is specifically a polynomial, then it is then it is Riemann integrable as well. So in this case, we'll move from Rs integrable to Riemann integrable, provided the function, the monotonically increasing function that we are considering, is a polynomial. So precisely, we'll be using some very good properties of the polynomials. So what do we know about polynomials? Polynomials are continuous. They are differentiable. Their derivatives are also continuous. That's why, in fact, all its derivatives are continuous. We call them as smooth functions, and they are the ideal functions that one can have. So yeah, let's see how we'll use this property and show that Rs integrability will lead us to the Riemann integrability, provided the function is polynomial. Solution. Oh, okay. Let alpha be a function defined on closed interval AB to R, be an increasing, or I should write a monotonically increasing, or monotonically monotonically increasing polynomial, and also we are given that this A to B fx d alpha x, this is finite. That means for any epsilon positive, there exists a delta positive such that this UPF alpha minus LPF alpha, this is less than epsilon, whenever norm P is less than delta. So let's mark this as equation 1. Okay. Now let P be the partition which is equal to A x naught less than x1 and so on up till xn, which is equal to B, be a partition of closed interval AB with norm P strictly less than delta. Then we need to show that this is Riemann integrable. That means UPF minus LPF is less than epsilon. So let's see how does our UPF minus LPF looks like. This is equal to summation I from 1 to n mi minus small mi xi minus xi minus. Now we will use the continuity and differentiability of the function alpha and hence use the mean value theorem. Let's see how. So since alpha is a polynomial, this implies alpha is continuous in closed interval xi minus 1 to xi. Alpha is differentiable in this open interval xi minus 1 to xi, and this happens for every I 1 to n, then by the mean value theorem, by mean value theorem, we can always find some ci in open interval xi minus 1 to xi such that this f dash ci is equal to fxi minus fxi minus 1 upon xi minus xi minus 1. Sorry, this is not f, no, this is alpha. We're talking about, we are applying mean value theorem on the function alpha. That means alpha dash ci is equal to alpha xi minus alpha y, sorry, xi minus 1 upon xi minus xi minus 1. And since the function alpha is increasing, this will always be positive because the derivative of an increasing function is always positive. So that gives us this mod alpha xi minus alpha xi minus 1. This is equal to, or instead we need not use this modulus because everything is positive, we know that. Alpha xi, this is equal to alpha dash ci times xi minus xi minus 1. Now, if I take m, also, um, since alpha is a polynomial, its derivative is continuous as well, and hence on closed interval AB it will be bounded. Also, since alpha is a polynomial, its derivative will again be a polynomial. Alpha prime is also a polynomial on closed interval AB. In fact, this will always be positive, because alpha is considered to be an increasing function on closed interval AB. This implies there exists some m positive such that alpha dash t will be less than equal to m for every t in closed interval AB. Or instead, since I need the infimum, I'll write this to be there exists small m and capital M positive such that small m is strictly less than alpha dash t, strictly less than m. Now, how can I say that the small m is positive? That is because our function alpha is strictly increasing. That means its derivative will always be strictly positive. So we can always find a lower bound, which will be strictly positive because alpha is not constant. If this lower bound is exactly equal to 0, in fact, it doesn't even have any critical point in between. Because if it had, then we could not say that this is increasing in whole interval close AB. So it must be strictly greater than some positive real small m. Now this gives us that this implies small m times summation I from 1 to n, mi minus ni, xi minus xi minus 1. This will be less than or equal to, also we can say less than equal to summation I from 1 to n alpha dash t. Or instead, I can also write, because this happens for all t, I can take specifically this t to be ci, the ci that we got using this mean value theorem. Okay, let me mark this as equation 2 and this one as 3. Mi minus mi, xi minus xi minus 1. This we got by equation 3. Okay, now This is equal to summation I from 1 to n. Now alpha dash ci is equal to alpha xi minus alpha xi minus 1 upon xi minus 1. Is equal to alpha xi minus alpha xi minus 1 upon xi minus 1 mi minus mi xi minus xi minus 1. This we are getting by equation 2. So here this gets cancelled out and we are left with summation I from 1 to n, capital Mi minus small mi, alpha xi minus alpha xi minus 1. And what is this? This is UPF alpha minus LPF alpha. So this tells us that the left hand side was small m times UPF minus LPF. That means m times UPF minus LPF. This is less than equal to UPF alpha minus LPF. That gives us UPF minus LPF. This is less than equal to UPF alpha minus LPF alpha upon m. Now, if in the equation 1, I would have taken this to be m times epsilon, where m is given here, then this would have been less than, strictly less than m epsilon by m whenever norm p is less than delta, and this comes from equation 1. Therefore, what do we get? We get UPF minus LPF is less than epsilon whenever norm P is less than delta. This tells us that this fx dx is finite. This is from A to B. That means if f is R is integrable with respect to some polynomial, some increasing polynomial, then the function f will be Riemann integrable as well. So I hope this proof is fine with everyone. If you have any doubt at any step, you can ask. So the given statement is true. Please go through the solution again. If you have any doubt, please ask. Okay, so if there is no doubt, we can move to next question. Question number 4, I think there is it is incomplete in some sense. I was not able to understand what they were actually asking. So I'll skip that. Let's move to question number 5. It says that let f close interval AB to R be Riemann integrable integrable state whether true or false for every t in close interval AB. There exists a function gt which is defined from close AB to R. We can find a function gt such that the function f is Rs integrable with respect to this gt, and this integral a to b fx dgx is equal to t to b fx dx. So basically we'll give an example of a function g that depends on t somehow, such that the function f is this Rs integrable with respect to this function gt, and its integral is given to be integral over t to b. So f is Riemann integrable, that means f a to b fx dx is finite. This implies, again, by definition, for any epsilon positive, there exists delta positive such that UPF minus LPF, this is less than epsilon, whenever the partition P is such that its norm is less than delta. If I consider the function gt to be gt defined from AB to R, where gtx, this is equal to 0 for x less than t, and this is equal to x minus t for x greater than t. Well, in that case, if we take the partition p equals to x naught, x1, x2 up till xn equals to p, be a partition of p such that its norm is less than delta and t is somewhere in between xg and xg minus 1. So xg minus 1 is less than equal to t less than equal to xt. So in that case, if we evaluate this, obviously t will be somewhere in between any of the point in the partition. So this u pf gt minus lpf gt will be summation I from 1 to n mi minus small mi gxi gt. Yeah, gtxi minus gtxi minus 1. Now, since this gt is 0 for all x strictly less than t, so up till xj minus 1, it will be 0. So this will be summation I from j to n mi minus mi gt xi minus gt xi minus y. And for x greater than equal to t, it is exactly equal to x minus t. So this will be, in fact, for uh, t greater than equal to j. I should write it to be j plus 1, no? I equals to j gt xj minus gt xj minus 1. So that will be plus mj, yeah, minus mj gtxj minus gtxj minus 1. Now gtxj minus 1 can be 0 or 1, 0 or, yeah, we will have to take something specific. So in that case, gtxj minus 1 is 0 and gtxj can be xj minus t, or yeah, it will always be xj minus t. So this is equal to summation I from j plus 1 to n mi minus small mi, and this is xi minus t minus xi minus 1 plus t plus mj minus mj xj minus t. So this t will get cancelled out. So this will be summation I from j plus 1 to n mi minus mi xi minus xi minus 1 plus mj minus mj xj minus t. Now this will obviously less than equal to, I'll mark this as equation 1, and this will be less than equal to summation I from 1 to n mi minus small mi xi minus xi minus 1 where p equals to x naught equals to a, x1 up till xn is, or instead I should write this to be y. This is some other new partition which is equal to the previous one for some terms. This is a equals to y naught, y1, so on up till yn equals to b, is a partition of p of this closed interval ab, such that this j minus 1th element is equal to t and y I is equal to xi for all I greater than equal to j. The rest of the terms included are just some positive terms, so obviously we can get this less than equal to. And yeah, and this peak, since this I since the norm of the partition P was less than delta, and P bar can also be, the norm of the partition P bar can also be made to be less than delta, because after Yj, rest of the terms are same. In fact, the earlier terms also we could have taken the same except for the Yj minus 1th term. So clearly, since this part norm of the partition P bar is less than delta, we get UPF GT minus LPF GT. This is less than equal to summation I from 1 to n mi minus mi yi minus yi minus 1. This will be, this is equal to UPF minus LPF, and this is less than epsilon. Because P is, sorry, because of this equation star. By star. That means this A to B fx dgx is fine. Or we can say that f is Rs integral. In fact, now let's look at what is the value of the integral? Integral is actually the infimum of UPF, and which is equal to the supremum of the LPF. So in that case, and A to B fx dgx, this is equal to infimum UPF UPFT, where P is the partition of AB, which is equal to infimum summation capital MI. So as we had done earlier, for any partition, the only term still here will be left. So this will be summation I from j to n x I minus x, where obviously xj is equal to t. And what is A to B? Sorry, this will be t. T to B fx dx will be again infimum of, we can, yeah, we know that this infimum exists because we know that this integral is finite, where P is some partition which is equal to infimum summation I from j to n mi xi minus xi minus 1, where xi is some partition whose first element is t. So that's why I'm taking from j to n. Because eventually, so that this gives us A to B fx dgx. Therefore, f is Rs integrable, and this A to B fx dgx, this is equal to T to B fx dx. Yeah, so the main idea was to take this specific G like this. So this is the important part. I hope this solution is fine. So yeah, therefore the given statement is true. We can always find, for every t, we can always find such gt. Gt is well defined for all t in close AB. So next, yeah, if you have any doubt, you can ask. Or else let's move to next question, question number 6. Question number 6. Again, state whether true or false. Sorry. Yeah. Mm. If f and g are two functions from closed interval ab to r, both are Riemann integrable. Riemann integrable. Then the function maximum of fg and the minimum of fg are also Riemann integrable. For this, if you can recall what you did in the class, that when we evaluate the integral via this Riemann sum approach, in that case, everything turns out to be similar to the algebra of limits. And in case of limits, if you can recall that we had done such type of sequences. If xn and yn are convergent, then maximum of xn and yn and minimum of xn and yn is also convergent. So basically, the idea is to use the fact that maximum of two values is given by a, suppose maximum of a and b is given by a plus b plus mod a minus b by 2, and hence using the algebra of limits. So yeah, and it's very good that this algebra of limits is used to see the Riemann integrability via the Riemann sum approach. So yeah, it's very trivial, so eventually this will be true. So let's prove how. We define the function hx to be maximum of fx and gx, and this is for every x in closed interval ab, and we know that this can be algebraically written as equal to fx plus gx plus mod fx minus gx by 2. Similarly, we have this in minimum of two values. Here we'll get minus. Hmm. So now since f and g are Riemann integrable, this implies this limit norm p tending to 0 SPF is equal to 0, which is equal to limit norm p tending to 0 SPG, where this SPF and SPG is the Riemann sum, which is given as follows, where SPF, this is equal to summation I from 1 to n FCI xi minus xi minus 1, where ci is arbitrarily chosen from the interval xi minus 1 to xi. Similarly, this SPG is summation I from 1 to n g ci prime, some other ci's, xi minus 1. Now, since this function, these functions f and g are integrable, then no matter what ci's or ci primes we take, as we take this norm p tending to 0, the limit should always converge to 0. So now using, and hence using the algebra of limits, we can see that this function, this limit norm p tending to 0 for the SPH will also be 0. Let's see in detail how we get that. Okay. Now, this SPH, this is equal to summation I from 1 to n FCI, where CI is independent. It's arbitrarily chosen between xi and xi minus 1. So by definition, this is equal to summation I from 1 to n. This is FCI by 2 plus GCI by 2 plus mod FCI minus GCI by 2 times Xi minus Xi minus. So this is SPF by 2 plus SPG by 2 plus summation I from 1 to n FCI minus GCI mod Xi minus Xi minus 1. And this can be written as less than equal to SPF by 2 SPG by 2 plus SPF, or instead we can say SPF mod F minus G by 2. Now since both SPF and SPG are converging to 0 as norm P tends to 0, so that will give us SP mod F minus G will also be equal to 0. Oh, limit now. So here we have limit norm P tending to 0. So taking norm P tending to 0 both sides, we get limit norm P tending to 0 SPH. This is less than equal to, rest of the terms are going to 0. So, and since SPH is always positive, so therefore we get limit norm P tending to 0 SPH is equal to 0. Therefore, the function h is integral. Similarly, we can define another function, say psi x to be fx plus gx minus mod fx minus gx upon 2. And using this exactly same approach, we get that the psi is integral. And hence the given statement is true. If you have any doubt, you can ask. Or else let me ask you to solve next question yourself, because yeah, that's very trivial whatever you did in your high school. Just use substitution method to evaluate the integral. Question number 7. Evaluate 2 to 4 sine root x by root x dx. Yeah, I want you to solve this yourself. I'll wait for 5 to 10 minutes. You can solve, then we will discuss. Yeah, meanwhile, you can go through the previous proof as well. If you have any doubt, you can ask. Okay, so this is nothing but just substitution. Firstly, we'll see that this integral is finite and then use our standard methods that we had studied in high school to evaluate this integral. So, since we know that -1 is less than equal to sine root x less than equal to 1, and for x in between 2 and 4, we get root 2 less than equal to root x less than equal to 2, which tells us 1 by root 2 less than equal to 1 by root x less than equal to 1 by 2. Sorry, this inequality will change. So this will be greater than equal. So this tells us that -1 by root 2 is less than equal to -1 by root x. This is 1, this is 2 by first and second. This will be less than equal to sine root x by root x. This will be less than equal to 1 by root x. And 1 by root x is less than 1 by root 2. So, therefore, what we get -1 by root 2 is less than equal to sine root x by root x less than equal to 1 by root 2 for every x in 2 to 4. And since this integral -1 by root 2 from 2 to 4 dx, this is just 1 by root 2, 4 minus 2, 2, finite, and 2 to 4, 1 by root 2 dx, this is 2 by root 2. So basically root 2, this is also finite. So by sandwich theorem for the integrals, we get that this integral 2 to 4 sine x by root x, this is finite. And then we will use our standard high school methods. Just take the substitution, denote I to be 2 to 4 sine x by root x dx. Sorry, this was sine root x now. Let t to be equal to root x. This gives us that dt is equal to dx by 2 root x. So the limit turns out to be root 2 to 2 sine t, and dx by root x will be 2 dt. And this will be, we know that this integral of sine t is minus cos t. So this will be cos t root 2 to 2. So this is just 2 cos root 2 minus cos 2. That was our option number 2 times cos root 2 minus cos 2 is option C. Therefore, the option C is right. I hope this is fine. If you have any doubt, you can ask, or else we are done with our today's assignment sheet. I'll wait for 5 minutes. You can ask your doubt, or else then we'll meet next Saturday. Okay, so if there is no doubt, let's end this session. We'll meet next Saturday. Thank you.